Hi students, I am Ramesh, Assistant Professor, Department of ECE, Sri Eshwar College of Engineering, Coimbatore. In this video, I am going to talk about metal oxide field effect transistors or MOSFET. Uh, this is second part of Module 5 field effect transistors in semiconductor physics course. MOSFET is broadly classified into two. One is enhancement type MOSFET, another one is depletion type MOSFET. In this video, I am going to talk about circuit symbol, construction, operation, drain and transfer characteristics of enhancement MOSFET. Next video, I am going to talk about depletion type MOSFET. Like JFET, MOSFET also has three terminals: source, gate and drain. MOSFET is also voltage control device, that is current flow between source to drain ID is controlled by gate to source voltage VGS. So current flow is controlled by applied voltage, so that is why MOSFET comes under the category of field effect transistors or voltage control device. Both this enhancement and depletion MOSFET of N type or N channel, so the electron flow is contributing current, that is majority carrier is contributing current, so MOSFET also unipolar device. Enhancement type MOSFET. So parameters what we are going to consider is ID, drain current. The drain current is given by VDS, drain to source voltage. Drain current is controlled by gate to source voltage, that is why MOSFET is called field effect transistors. Terminologies. Capacitance effect is one of the important terminology in MOSFET. So this is going to create a channel between source to drain, that is going to create current conduction in MOSFET. Inversion layer and threshold voltage. The gate to, as fit the name suggests, gate to source voltage controls the flow of current. When gate to source voltage is lesser than threshold voltage, there will not be any channel formation. When gate to source voltage is less than threshold voltage, even though we apply drain to source voltage, there will not be any current flow. When gate to source voltage is greater than or equal to threshold voltage, channel is formed between source to drain. The channel formation, otherwise called inversion layer, the inversion layer is formed between source to drain. Then if we apply drain to source voltage, there will be current flow between source to drain. That current is termed ID, drain current. So enhancement type MOSFET or E MOSFET is having two types. One is N channel, next one is P channel. The arrow mark represents the flow of electrons inside MOSFET. Construction wise, basically we'll be having a p-type material, p-type semiconductor bar. In this n-type heavily doped n-type bar would be diffused. Here also we have n-type heavily doped bar would be diffused. This p-type material would be lightly doped compared with these two n-type material, above which we'll be having a silicon dioxide layer. Using metal contact, a contact would be created for drain and source. So this is source part, this is drain part. Above silicon dioxide layer we'll be having gate. So this gate is metal part. This side we'll be having p-type semiconductor. So this p-type semiconductor and metal is going to create a capacitive effect. In between we will be having a silicon dioxide layer. This is going to act as dielectric. So this particular part is going to create a capacitive effect in N channel enhancement MOSFET. as we knew, so here the mass structure is acting as parallel plate capacitor. So this top plate is going to act as positive plate. So here we are assuming this as p-type substrate. So here we are going to give positive polarity of the battery to a gate, and negative polarity of the battery is going to be connected with p-type substrate. In between we will be having silicon dioxide that is going to act as dielectric material. So if we apply electric field, what will happen? The number of holes would be accumulated in gate. If we have n number of electrons accumulated in the gate, n number of, sorry, if we have n number of holes, not electrons, if we have n number of holes accumulated in gate, equal number of electrons would be accumulated in the p-type substrate. So this p-type substrate is in between the source and drain. So this is how we are creating a channel between source to drain, like this. So here VGS, positive terminal of the battery is connected with gate, and negative terminal of the battery is connected with p-type substrate. So when we increase this potential here in metallic plate, holes would be accumulated. If n number of holes accumulated in the plate, n number of holes would be attracted from this p-type material near to this dielectric material. So this attracted electrons are going to create a channel between source to drain. So this is drain. So drain is connected with VDS, that is positive terminal of the VDS. So drain is reverse biased, gate is forward biased. Gate is n-type material, it is connected with negative polarity of the battery. Drain is n-type material, but it is connected with positive polarity of the battery. So drain is reverse biased, gate is forward biased. So here important concept is when VGS is less than threshold voltage, when VGS is threshold voltage, even though we apply drain to source voltage, there will not be any current flow because we don't have any channel width, or we do not have any inversion layer. So when VGS is equal to or greater than threshold voltage, there will be channel between source to drain. Then if we apply VDS, there will be current flow between source to drain. That current is termed drain current. As I said previously, when VGS is less than 2 volt, here we are assuming threshold voltage is 2 volt. So when we increase VGS, when VGS is less than 2 volt, there will not be inversion layer between source to drain. Even though at the time, even though when we apply VDS, there will not be any current flow. So this region is termed cutoff region when we are applying VGS greater than 2 voltage. Assume that we are applying VGS equal to some 6 voltage. So when VGS is greater than 6 voltage, there will be channel between source to drain. So this drain to transfer characteristics curve is drawn between VDS, drain to source voltage, versus drain current. When we increase VDS with respect to constant VGS, now VGS is greater than threshold voltage, so channel inversion layer is formed between source to drain. Now if we increase VDS is the reason for ID. So when we increase VDS, ID will increase up to certain point. The certain point is when VDS, when drain to source voltage becomes pinch off voltage, VP. When drain to source voltage is equal to VP, ID, drain current is saturated, or it became constant. Transfer characteristic curve. So this characteristic curve is drawn between VGS versus ID, gate to source voltage versus ID. Assume that we are applying or we are keeping VDS, drain to source voltage, equal to 5 voltage. Even though we have drain to source voltage as 5 voltage, there will not be any current flow because of there is no inversion layer between drain to source. Now, as we knew, for this MOSFET, the threshold voltage is 2 voltage. So now we are applying VGS, positive VGS. When VGS is equal to 1 voltage, at that time we do not have any channel between source to drain. When VGS equal to 2 voltage, there is a channel established between source to drain. Now when we increase VGS, what will happen? ID also gets increases. Thank you for watching.